Welcome to solverfy.
In this image, we have 4 stages of phosphoric acid being titrated with NaOH. What that means is we have phosphoric acid in this beaker down here. So phosphoric acid, or H3PO4, is the analyte, and the titrant is NaOH, which is in the burette up here. Our goal is to arrange A, B, C, and D into chronological order. Our first step at the very beginning of the titration, before any NaOH is added, we have a beaker full of just H3PO4. The red spots are phosphate groups, and the smaller blue ones are hydrogens. So these images right here with 1 large red spot and 3 smaller blue ones is the original phosphoric acid that we begin with. So we know that our initial beaker will look like C with all H3PO4 molecules. Once we start adding NaOH, the hydroxide ions from the NaOH will react with H3PO4 to create water and H2PO4-. So when we start adding NaOH, we'll have some H3PO4 and some H2PO4- in our beaker, and that is beaker B. So that's our second step. If we keep adding NaOH, it will react with all of the H3PO4, and we'll eventually be left with only H2PO4-. Then the excess hydroxide will react with that H2PO4- to form more water and HPO4 2-. And in this stage, we'll have some H2PO4- and some HPO4 2-, which is stage D. Then, as we continue adding NaOH, the hydroxide will react with all the rest of the H2PO4-, and we'll be left with only HPO4 2- at the very end, which is the last beaker, letter A. So our final order of the scenes is C, B, D, A. In the second scene, scene B, we are in the middle of this top reaction where we have some H3PO4 and some H2PO4-. Since these are a conjugate pair, we can find the pH of the system using the Henderson-Hasselbalch equation. So the pH is equal to the pKa of, in this case, H3PO4, plus the log of the buffer component concentration ratio, which is the concentration of the conjugate base, which in our case is H2PO4-, over the concentration of weak acid, which in this case is again H3PO4. If we look at image B, there are 3 molecules of H2PO4- and 3 of H3PO4, so there's a 1-to-1 ratio of the 2 molecules. That means this fraction here is 1/1, or just 1, and the log of 1 is 0, so the pH is just equal to the pKa. The Ka1 of phosphoric acid is 7.2 times 10 to the negative 3, so the pH is the negative log of 7.2 times 10 to the negative 3. And this is 2.14. Now if we need 10 milliliters of NaOH to get from scene C to B, then that means we need 10 milliliters of NaOH to pull off 1 hydrogen from half of the phosphoric acid molecules. So to convert the remaining molecules of H3PO4 to H2PO4-, that'll be another 10 milliliters of NaOH. Once we've done that, we'll have a beaker full of just H2PO4- molecules. And in order to get from there to scene D, that's going to be another 10 milliliters of NaOH, since we're pulling off a hydrogen off of another half of the molecules. And then to go from scene D to scene A, we're again going to pull off the hydrogens from the second half of those molecules, converting the rest of the H2PO4- to HPO4 2-, which will bring us to scene A. What that means is that the additional NaOH needed to go from scene B all the way to scene A, or the second scene to the final scene, is 30 milliliters of NaOH.